Now we shall define upper and lower sum for a function. I have written the definition here. We shall see the meaning of this. Let f be a bounded function on a closed bounded interval a comma b. Now hereafter we are considering f real valued bounded function, and the interval is of real numbers. Let sigma be any subdivision of the closed interval a comma b. We define u, capital U, f on sigma, called the upper sum for f corresponding to sigma as upper sum of f corresponding to sigma is equal to summation k takes value 1 to n capital M of f comma ik into length ik, where I1, I2, In are component intervals of sigma. And similarly, the lower sum is defined as lower sum for f on sigma is equal to summation small m of f on ik into length of ik. Now, what is capital M that we have defined earlier? So, capital M of f on an interval ik will be LUB. So, least upper bound of f of x belongs to ik, the interval, that is the meaning. And that means roughly capital M denotes the maximum value of the function in the interval ik. And similarly, what we have defined earlier is small m of f on ik is GLB, greatest lower bound when x belongs to ik of the function f of x. GLB of f of x when x belongs to ik. That is the meaning of capital M and small m. And we have to for upper sum we have to take the summation of the product of maximum value of the function into the length of the interval. This denotes length of the interval. So that means if I1, I2, In are component intervals. So here this is the interval, closed bounded interval AB, and that is divided into components. The components we have denoted by I1, I2, etc. and In. So this is these are the components, parts or subdivision. Subdivision of the closed interval a comma b is like this, and the last is In. And for each subdivision we have to take this product, and so therefore actually upper sum of f on sigma will be if you take k is equal to 1, the first term is m of f on I1 into length of I1 plus, so that means the maximum value of the function in this interval into the length of the interval plus similarly the maximum value of the function in the second interval into length of the interval, and so on, that is continued, and the last we will get maximum value of f on In into length of In. So this is the meaning of the upper sum. Similarly, the lower sum will mean lower sum of for f on sigma, the same subdivision will be, instead of capital M we have here small m. What is small m? The greatest lower bound of f of x. That means the smallest least value of the function in the interval. So in each interval we have to, for upper sum we have to take the maximum value multiplied by interval length of the interval and add this up to n terms. So similarly for lower sum we have to take the minimum value of the function in each interval, and that we have denoted small m f on I1 into length of I1 plus, and that is continued up to small m of f on In into length of In. So this is the meaning of the lower sum. Now we shall see what is the geometrical meaning of this, and clearly now you see what is the relation between upper sum and lower sum. Here we take the maximum value and we multiply by the length of interval. It is the same length of interval. We also for lower sum we take the minimum value and multiply by the length of interval, and therefore obviously this upper sum will be greater than or equal to lower sum. So we mention it as obviously upper sum, every upper sum, we will prove this result also, upper sum is greater than or equal to lower sum of f on subdivision sigma. Now we shall consider geometrical meaning of this. We write as a note or remark, and for that purpose we shall draw a figure. So here it is the upper sum we have written. Suppose this is the function that we shall denote in graph of the function. Say these are the axes, x and y axis, and suppose the function has graph of this type, and this is the interval a to b. We will consider this is a, and we will take the function in the interval a to b. Now we divide this interval in parts as components. Earlier we have defined. So this is I1, let this be I1, I2, etc. Let it. So this is what is I1, this is I2, and last will be IN. These are the component intervals. Now what we have to consider is for the upper sum. For the upper sum, we have to consider the maximum value of this function in this interval. Now the functions, this function is y is equal to f of x. This is y is equal to f of x, and that means y is the value of the function, or the ordinate at every point is the value of the function. That means at a, this is the value of the function. So this part we have considered, and so in this interval where the function is maximum, now we can see in this interval in I1 at a, the value of the function is this much, and at this point the function has this value. So function is increasing, and therefore in the first interval this is the maximum value of the function, and therefore we have to take that value as maximum value of the function occurs here, and therefore this is the maximum value and multiply it by length of I1. So therefore we have to complete this rectangle, and we will get this value. This is the first term, that is the area of this rectangle. Maximum value of the function in the interval I1, that is this much, because here it is maximum, and multiplied by I1 means that the first term will be this height into this breadth, and that is the area of this first rectangle. Similarly, what will be the second term, that is maximum value of the function in I2 multiplied by length of I2, and here again see the function is increasing, and therefore this is the maximum value, and therefore this will be the maximum value of the function in I2 multiplied by I2. Similarly, we can complete this here also, this is the maximum value, and but here you see this is the maximum value because the function is decreasing in this interval I3, and here this is the maximum value of the function. So in this way we have to consider these rectangles, and for the last this is the maximum value, here it is the maximum function, and therefore the upper sum means the first term represents the area of the first rectangle, this represents the area of the second rectangle, height into breadth, that is the area of the rectangle. Similarly, third term represents the area of this rectangle, and last term represents the f of f on I1 is this height, that is maximum at b. The function is maximum at b, so we have to take the maximum value in the whole interval and multiply it by length of IN. So that is the last rectangle, and thus this represents the upper sum. Area under covered by these rectangles will be the upper sum, or that this area will be the upper sum. So we can see area of the sum of the areas of these rectangles will denote the upper sum, and here it is. So this is the upper sum. So upper sum of for f on sigma. And now we shall see what will represent the lower sum for that. And for lower sum we shall consider the same figure, and what we have to take is the lower value, or lower means a minimum value of the function in this interval, and we will draw another figure for this, and that is the same function is to be considered, same subinterval is to be considered, and we will have like this. See, this is y, and I shall try to draw the same function as above, you should see, and then this is again a and this is b. So the intervals, as earlier we can denote I1, I2, etc. It is again not necessary that these intervals must be of equal length, may be or may not be. And here this is I1. So what we have to consider is for the lower sum minimum value of the function in the first interval, and you see the minimum value of the function in I1 occurs at this point. So this a point, and that is the minimum value. So we have to consider the interval as this one. This is the minimum value, this is the maximum, at this point it is maximum, at this point it is minimum. So we have to consider minimum value multiplied by I1, and that will be the this value, or I shall denote it as like this. This is the value. And next, what is the minimum value in the second component or second interval? That will be this one. Minimum, this is maximum, this is minimum. Similarly, this is minimum, and this is the minimum value. So these are the minimum values of the functions. And now the area of these, sum of the areas of these rectangles will be the lower sum. So that will be the area covered by this, or sum of the areas of these rectangles. And we can see which area is bigger. Obviously this area, this is the area which is of circumscribed rectangles. That means we taking maximum height in each component, and this is the area, sum of the area of the rectangles considering the inscribed rectangles. This is this represents lower sum of E upon sigma. So that means geometrically we will mean. So this is the meaning of lower sum and upper sum. So we have to understand what is the meaning of this summation, geometrical meaning of this. If the interval is divided in components I1, I2, etc., then upper sum. So geometrically upper sum represents is the sum of the areas of circumscribed, means which lies above the curve, and for this it is lower sum is the sum of the areas of inscribed rectangles. These rectangles are below the curve, these rectangles some part is above the curve. Sum of the areas of the circumscribed rectangles, and lower sum is the sum of the areas of the inscribed rectangles. So this is the geometrical meaning of upper and lower sum, and this is the definition that we have to remember: upper sum and this is lower sum. And we must note that upper sum is always greater than or equal to lower sum. Now what happens if we consider see the refinement of a division. refinement of a division that we consider, and if we consider the refinement, that means if we make this increase the number of components. Refinement of subdivision means subdivision obtained by including more points of division, and that means we reduce the length of this components. So this will be again in adding this. So this is the refinement, and when we take the refinement, the intervals are increased, and see if I1 is split in two parts, these two parts, then here the first term will be length of maximum height of this in this interval of the function, that is maximum value of the function will be this much, and that means this part is excluded, and maximum value of the function in the second component will be this one. So that means this part will be deleted. And similarly, if we make the refinement for this, see the last interval, if I increase the point of division, that means this is the point of division increased, in is divided in two parts, then what is the maximum value of the function in this component is this much, and maximum value of the function in this part is this one. So that means this will be the sum of the areas of the two rectangles. That means this part is excluded, and therefore if we take the refinement of a subdivision, the upper sum decreases. Upper sum decreases. That we are going to prove it in our next lemma. And similarly, if we increase the number of division, that means if we take the refinement, what happens to lower sum? For that purpose, if I consider I1 is split in two parts, then what is the minimum value of I1 first interval? That is the same here. So this is the minimum value, and therefore this rectangle will be the same. But for this second interval, the minimum value occurs at this point, and therefore we have to consider this value. So that means this interval, this part will be added if we take the refinement. This is added in the if we divided I1 in two parts, and thus this happens for each. That means if you take the refinement, lower sum increases, or for the last interval you see this B is there, and if I add one more point of division, then the rectangle in this component will be the same, this one, but rectangle in this component will be this one. The lower value of the function is this one, and therefore further so we have to consider this part is added in the sum, and therefore if you take the refinement, lower sum increases and upper sum decreases. So you should verify this. Now we shall state and prove a lemma. It is a lemma, and it is lemma number 1. Let f be a bounded function, real valued function, bounded function on closed interval a comma b. F be a bounded function on closed interval a comma b, then every upper sum for f is greater than or equal to every lower sum for f. So that is what we have written earlier, and we can verify from this figure, or that is if sigma and tau are any two subdivisions of the closed interval a comma b, then the result is now upper sum of f on sigma is greater than or equal to lower sum for f on tau. The subdivision may be different or may be the same. Here for upper sum we have taken subdivision sigma, and for lower sum we have taken subdivision tau. Then also the upper sum is always greater than or equal to the lower sum. Upper and lower sum we have defined here earlier. Now we shall prove the result. So we shall first prove that if sigma star, we will consider the refinement as we have seen here. If first we shall show that, or we shall prove that if sigma star is, or the sigma asterisk, sigma star is any refinement of sigma, means it is obtained by adding more points of division in sigma, and tau star is any refinement of tau, then upper sum for f on sigma is greater than or equal to upper sum of f on sigma star, and lower sum of f on tau is less than or equal to lower sum of f on tau star. See what we have written. That is, if you consider refinement, the upper sum decreases. Yes, upper sum decreases. So the upper sum is greater, this upper sum is greater than this one. So in the refinement upper sum decreases, and in the refinement lower sum increases, as we have seen here, because we delete this part. So the in refinement, this part of the rectangle, this part of the rectangle will be deleted, and the upper sum will reduce in refinement. If you add the more subdivision, the upper sum decreases, and if you add the more subdivision, this part will be added, this part is added, this part is added, that means lower sum increases. So in the refinement, so in or any refinement of subdivision, of a subdivision, or yes, a refinement of any refinement of subdivision, the upper sum decreases, and the lower sum increases. Now we shall consider refinement for sigma first. We shall prove this result, and similarly this will follow. And here what is to be considered is sigma star is refinement of sigma, and let sigma star be obtained by adding one point of division. Only we will add one component in sigma, that will become a refinement. Now it is enough to prove. It is enough to prove the case in which sigma star is obtained from sigma by adding only one point of subdivision. How we will consider this? Let sigma has this, let the subdivision sigma has components. See, the components we will consider for this subdivision sigma as I1, first component, and so on, Ik, the kth component, and so on, In be the components of sigma, and let the subdivision sigma star, let sigma star has the component intervals, we can say component intervals, and this has component intervals. We want to only add one point of division, and we divide ik in two parts. So remaining we will not change, remaining components will be as it is, that is I1 will be as it is, and this ik is split in two parts, ik star and ik double star or I asterisk and in. So thus what we have done is this one, that is, now see, this is if the interval is AB and this is I1 first, and here it is ik and this is in, this is a sigma, and in sigma star what we have done is I1 is the same and every interval is the same. So only this ik is split in two parts. The first part is ik star and the second is ik double star. So this ik is divided in two parts, and thus where ik is union of ik star and ik double star. Similarly, the length of ik, what will be length of ik? You see, length of this is ik, length of ik, it is union of these two these two components, and therefore the length of ik will be length of ik star plus length of ik double star. So that is length of ik star plus length of ik double star. So thus we have this. Now we will form the upper sum on sigma star. Now upper sum of f on sigma star. How to obtain this? By definition, that is this is sigma star, this is sigma, and this is what is sigma star. So this subdivision we have to consider, and that will be summation this I1, maximum value of m on I1 into length of I1, etc. by definition. So this we can consider, or we can write in summation notation as summation j takes value 1 to n, maximum value of f on ij into length of ij. See, but we will delete here j is not equal to k, because this we will don't consider, and we will write it separately. So this means summation takes 1 to n. So maximum value of f1 on I1 into length of I1, maximum value of f on I2 and length of I2, and so on. So why we have not considered k? Because if you consider k, then that will be of sigma, but this kth interval is divided in two parts, and therefore we shall write its sum separately, that is plus, this is plus, so maximum value of f on maximum value of f on ik star into length of ik star plus maximum value of f on ik double star into length of ik double star. So this we will write, but we should one more thing we should mention here is, so what we have is the maximum value of f on ik. So I shall write here itself. Before that we will note this, we have, see, this we have written, and we have maximum, see, ik star is subset of ik. See, this is ik and ik star is subset of ik. Therefore maximum value of f on ik star will be, what is relation between maximum value of f on ik? You see, maximum value of f in this ik star and maximum value of f on this ik. So ik is bigger than ik star, and therefore maximum value in ik will be also greater. So therefore this is the maximum value in the smaller interval will be less than or equal to maximum value of f on ik. And similarly the same thing happens for ik double star. Similarly, maximum value of f on ik double star is less than or equal to maximum value of f on ik. See, ik double star is subset of ik, and therefore maximum value of in this part will be less than or equal to maximum value on the interval, bigger interval. So these two things we have to note, and now we will use it here. So this maximum value of f on ik star is less than or equal to maximum value of f on ik, and this is also maximum value of f on ik double star is less than or equal to maximum value of f on ik. And thus this relation, now we are replacing these two by this the right side, and therefore the relation becomes less than or equal to summation j takes value 1 to n, j is not equal to k, maximum value of f. You should understand what we have written here, sum of the components except this part, and this is written separately. This is the definition that we have for upper sum. And now what we are going to do here is these two we are going to replace by maximum value of f on ik. The interval we represent bigger, and therefore this value, the above expression will be less than or equal to the below expression if you write this as maximum value of f, or I shall write below maximum value of f on ik into bracket. Now in bracket I shall consider the sum of this ik star plus ik double star. See, it is this is taken common, and that is replaced by maximum value of f on ik, and because both are less than this, and the interval we have added in the bracket. And what is this? This is same as ik. This is same as ik. You see here ik star, see that is it is length. We should write length of ik star, length of ik star plus length of ik star double star. And what is length of ik star plus length of ik star? That is length of ik, and therefore this is length of ik, and that this becomes equal to, now this is mfik into length of ik, and therefore here j we have not considered equal to k, and here we have written the term separately for j. That means this is exactly equal to, so we will write here this is exactly equal to summation j takes value 1 to n, maximum value of f on ij into length of ij. Here now all terms are included. Here it k is not included in this sum, but k is this sum, and therefore this now 1 to n including k, because this is length of ik. And what is this? This is the upper sum, definition of upper sum for f on sigma subdivision, and thus we have obtained this. Now I hope you can understand this. The upper sum for f on sigma star we have expressed like this, taking these components, this is sigma star, but then this term k term is written separately and not included in this summation. And further we have replaced these two values by greater value m, and we have taken this these intervals in bracket, and the addition of these two intervals is k length ik. I have not written that step, but we should note it, and that means the whole summation including k also, and taking j taking value 1 to n, which is the sum of the intervals earlier we have considered in sigma subdivision sigma, upper sum for subdivision sigma. And thus we have upper sum, see this upper sum for f on sigma star is less than or equal to upper sum for f on sigma, or that can be written as upper sum for f on sigma is greater than or equal to. This is less and this is greater. So, reverse changing the sides, we can get the inequality as upper sum for f on sigma is greater than or equal to upper sum of f on sigma star, and this we will suppose as 1. Now, the similar result holds in reverse way. If you take the lower sum, then the lower sum will increase if you take the refinement. So, what we have written earlier is tau star is a refinement of tau. So, similarly we have we will have lower sum for f on tau is less than or equal to lower sum for f on tau star. Because if you divide the interval C ik interval in two parts, ik star and ik double star, if you take the maximum minimum value, that is lower sum, minimum value of f on ik star, then that minimum value of f on this interval is greater than or equal to minimum value of f on bigger interval ik. So, that is the change in this, because the function may be here having greater value, and then function may be decreasing. So, therefore, the results will be reversed in case of minimum value. You can see the figure and check it. So, this is minimum value of f on ik star will be greater than or equal to minimum value of f on ik, and thus because of this inequality will reverse. This inequality will reverse. That means this lower sum, in case of we take the lower sum, then lower sum will be less than or equal to lower sum of f on tau star. And now we can, or that can be written as, or lower sum of f on tau star is greater than or equal to lower sum of f on tau, and we suppose this as second result. Now, if you take sigma union tau is, then it is a refinement for both sigma and tau, is the refinement, or is a refinement of both sigma and tau. Therefore, from 1 and 2, we have, see what the 1 gives. If you take the refinement, the upper sum decreases. So we can write like this. We take this as upper sum of f on sigma, and that is greater than or equal to this sigma star we shall replace by sigma union tau, because that is a refinement. Sigma star is refinement, this is also a refinement, and therefore I shall replace this sigma star by upper sum of f on sigma union tau. And again every upper sum is greater than or equal to lower sum. So, I shall write upper sum of f on sigma union tau is greater than or equal to lower sum of f on sigma union tau, and but that sigma union tau is refinement, and therefore that will be greater than or equal to lower sum of f on tau. So, thus we have this combining 1 and 2, starting with this, replacing sigma star by sigma union tau, and we get the results combining this. That is, see the first sum, upper sum of f on sigma is greater than or equal to lower sum for f on tau. First expression is greater than or equal to the last expression. These are the middle refinements we have written, and this is what we wanted to prove. So, this proves the lemma. Thus, we have proved the result, which is important. Every upper sum is greater than or equal to lower sum for f. And if you take the refinement, upper sum decreases and lower sum increases. So, thank you for watching the lecture. Next time we will continue the next part. Thank you.